So let's explore the structure of glycogen, how it's broken down, and how it is built up. So we've already seen this figure on the left here of what glycogen looks like. In each of these little units here, those are glucose units that are linked together. And it has the structure shown here on the right, if you were to zoom in, where we would have, in many instances, those glucoses are linked together through the alpha 1,4 linkages. And that's what sort of creates the linear structure of this. But then every so often, every 3 to 6 or 8 or so glucose units, we have a branch point, which is an alpha 1,6 linkage. If you recall from before, that's what causes the branching, this highly branched structure that glycogen has. The end result here is that we have many non-reducing ends. And so remember we talked about polysaccharides having reducing ends and non-reducing ends. And it turns out that the enzymes that are going to break down glycogen will remove sugars, glucose units, from those non-reducing ends. So having a great number of non-reducing ends in this highly branched structure allows for fast degradation. So we can say that enables fast degradation. And so you can imagine if this were one linear strand, rather than being branched, you'd have one non-reducing end, and it would take the enzyme a long time to access all of those glucose units. So let's explore how this happens in a little bit more detail. So the breakdown of glycogen, which we've called glycogenolysis now, so that literally means the splitting, lysis means splitting of glycogen, is carried out by a few different enzymes, and we're going to focus mainly on one called glycogen phosphorylase. And this breaks down the glycogen, like I said, from the non-reducing end, and it's going to yield individual units of glucose 1-phosphate. And so that overall reaction is going to look something like this, where we have a molecule of glycogen, and we're going to say that it has n number of units. So that could be 12, it could be 30, it could be a couple hundred. It's however many units of glucose it has. That's what the n means. A phosphorylase enzyme is an enzyme that's going to take a free inorganic phosphate group like this and add it to a molecule. And so that's what glycogen phosphorylase will do. It's going to take that phosphate group and add it to a new molecule of glucose that is taking off of glycogen. It can add that phosphate because it has energy stored in that glycogen molecule that it can access. And so the product then, again, will be glycogen, but now it's not going to have n units of sugar. It's going to have n-1, and it will have generated, or the enzyme, I should say, will have generated a molecule of glucose 1-phosphate. So let's be clear, this is glucose 1-phosphate. Now, glucose 1-phosphate is not something that we've really seen, and in fact, in order for this to be useful, it has to be converted to something that we're more familiar with, like glucose 6-phosphate. So there's an enzyme, and we don't have to worry about what the enzyme is, but it gets converted into glucose 6-phosphate, and again, that's that central metabolite that's so useful. And then it can then be converted into glucose, and it can be exported to the bloodstream. Now, this part where it's being converted into glucose and exported, this only happens in the liver. So from here on here is only in the liver and a couple other tissues as well. But what we're going to explore later on is that this does not happen in the muscle tissue. Muscles will use this glucose 6-phosphate directly because this can then be fed into glycolysis. But the liver, its job will be to export that out into the bloodstream. So that's how glycogen is broken down and how those glucose units can be accessed for our metabolic needs. But how is glycogen made? And this is called glycogen synthesis. And an interesting aspect of this is, remember I said that there is enough energy stored in glycogen to put an inorganic phosphate group on there. And so that energy is stored in glycogen. It had to have come from somewhere, and it ultimately has come from a molecule of UTP. So let's kind of explore in general terms how glycogen is made by this enzyme, glycogen synthase it's called. It's the important enzyme in glycogen production. Again, it starts glucose 6-phosphate. It will work with an enzyme. There's a couple of steps here that we're kind of leaving out, but a molecule of UTP is consumed, and it results in the production of a UDP molecule. And so just like before, we've seen that ATP can be used as an energy source, and that's true here with UTP. So just to make a note that UTP equals ATP in terms of energy. It still has that phosphoanhydride linkage that can be cause that phosphate group to be transferred to things and make that happen favorably. So anytime we see UTP being consumed, think of it just like ATP as well. Then, again, we'll leave out a few steps, but the point is that the glycogen synthase can take these materials, the glucose 6-phosphate and the energy from UTP, and it can produce glycogen. It can add on a glucose unit to make glycogen, and this will just keep happening to make that glycogen however long it needs to. So what I want to do is return back to our chart, our roadmap, because I want to add a couple of things to this now that we know a few things about the way that glycogen is produced. So just like we said a second ago, in order to make glycogen, we have to consume some energy, and that's in the form of -1, or we're consuming a molecule of UTP, okay? And that means that producing glycogen from glucose 6-phosphate ends up costing us a little bit of energy. But as we saw in the previous notes, when glycogen is broken down into glucose 6-phosphate, that glycogenolysis pathway does not yield that UTP back, okay? It's a zero-sum game when we're going from glycogen to glucose 6-phosphate.